Welcome to the lecture on statistical mechanics. Here we solve five basic problems. It's standard problems. In fact, this will give a good foundation for understanding the statistical mechanics more. First question is that derive the expression for the entropy of an ideal gas as a function of volume. And we know the equation PV is equal to NKBT. So PV is equal to NKBT. Here, N is nothing but Avogadro number. So basically, this is molar volume. So for 1 mole, we are doing calculations, but it doesn't matter. The expression remains the same. Mm, yeah. So from thermodynamics first law, we know that du is equal to delta Q plus delta W. So don't get confused with conventions. Rather, understand the conventions as this is change in internal energy. So when we are writing the equation in this manner, delta Q is heat added to the system. Heat added to the system, and delta W is also plus. So that means work is done on the system. And when we take work is done on the system, then delta uh, W would be minus PdV. So this is the work done on the system. Now from this we can write delta Q is equal to delta W is minus PdV. If we take that side, it will be du plus PdV. So basically, this is the our first law of thermodynamics, and the second law is second law relates to the entropy. So it determines the entropy. The change in entropy Ts is equal to heat. If we have given the condition, heat added to the system in a re- along a reversible path by temperature T. Okay, so yeah, this is the thing. Now we can substitute that delta heat added to the system is du plus pdv by T. And for ideal gas, we know that internal energy U is equal to F by 2 N kBT. So for 1 mole, I'm considering. And so ideal gas, monoatomic gas, F will be 3. So U is equal to 3 by 2 NKBT. Whether we remember that entropy is a extensive property. So when volume gets double, the entropy also gets double. Sorry, yeah, of course, when the volume gets double, entropy doubles. But I mean to say that as the number of gas molecules suppose doubles, then entropy also uh, will change accordingly. It will also get doubled. Yeah. So U is, but we have to calculate du. Now U from here for an ideal gas, it is only the function of temperature. So basically internal energy is depending on the is nothing but the total kinetic energy of the molecules. We know that there is no molecules interaction, so potential energy is zero, and yeah, so that's why the internal energy is only kinetic energy, which is given by F by 2 nkbt, which is only function of temperature. So du will be zero because the temperature is constant, and we are calculating as a function of volume. So P by temperature is constant. So pressure and volume both will vary in this case. Hence du equal to 0. So now we can write here ds is equal to pdv by t, and so ds is equal to p by t. We have to get from the first law, that is, sorry, from here, here p by t is nothing but p by t is equal to n ab by v. So n ab by v, this is entropy. So we have to calculate entropy as a function of volume. We can do as integrating. So S naught is the initial, and see, entropy is a state function. So initial value of entropy I'm writing as S naught. It is depending on the initial state of the system, and here entropy and, sorry, ds here. From this we get S is equal to uh, n kb ln v. Note that entropy is a function, is a state function, so it depends on that particular volume. For example, at this instant the volume is some example 1 liter, so the entropy depends only on that 1 liter. Plus yes not. So on what factors does S naught depends? It depends on the initial internal energy and number of particles. Like if not, it is function of internal energy and number of particles, molecules. So that can be figured out based on the given system and conditions, that is state of the system. Now so this is what our final answer is for the first question. Entropy variation with volume. How the entropy varies with volume. Note that the uh, temperature is constant in this case. Now we have the second question. Consider two molecules adsorbed on a two-dimensional square crystalline surface. Square crystalline surface means it has length and breadth would be equal. So the number of lattice sites in horizontal direction would be same as vertical direction. Each molecule can occupy one state and they interact only if they are adjacent, contributing to a negative potential energy. If the molecules are not adjacent, the total energy is zero. That is they don't interact. Determine the number of microstates for equal to zero. That is when they don't interact, when they are placed non-adjacently, and when they are adjacent, we have a potential energy minus zero point 0.5 volts. So, what is the number of microstates we have to determine for both the uh, things? So periodic boundary conditions are given. So that means if they are adjacent uh, and if they are not adjacent, so the number of sites that are given are 100 and we have two molecules. So I'm just taking for suppose 4, like I'm taking 16 instead of v equal to 100. I'm taking 16 like this. Now let's see how many possibilities for being adjacent. So here this can be adjacent, and likewise here. Um, what I would like to firstly I would like to consider the case of identical particles. In the question, it will be specified clearly whether the particles are identical or non-identical. But in our case, let's consider both. First, let's solve with identical, then non-identical. So if it is identical, then the particle, let's call the particle name as A because all particles are same. The two molecules are same, so A and A. Yeah, this is also A. So here we can place A and A here, or we can interchange A and A. So this will be one possibility. Similarly, another possibility 2, 3. Likewise, we have same here also. So 4 times and this is 3. That is 4 minus 1. Yeah. And similarly, in this manner also we have A or A here. One possibility, 2 and 3. So in the vertical direction also we have 4 into 3. So that means 3 is nothing but under root v minus 1. So let's calculate this. N is equal to under root v. Now this is nothing but 3 is nothing but n minus 1. That is here for this case v is equal to 16. So n is 4. 4 minus 1 is 3. 3 and into 1, 2, 3, 4 rows. So n rows. Plus in vertically also we have n minus 1 times 4 columns. So this will be 2n into n minus 1 In that case, how many? So, what I'm calculating for these identical particles is sigma epsilon. This will be is equal to 2n into n minus 1. And here we have given v is equal to 100 for actual question. V is equal to 100. This means n is equal to root v, which is 10. Then sigma of E is equal to epsilon naught when those the number of microstates corresponding to this energy occurrence is 2 into 10 into 10 minus 1, which is 20, 360, I guess. Yeah, 29 ja. No, it's not 360. 9 10 ja 92, 180. Now, how about the total number of microstates available? Total number of microstates available. So we have two molecules and 100 sites. So we can place them like in probability you might have read, or you can understand here 100 factorial by okay, let me write that full equation. B factorial minus b minus 2 factorial, because two molecules. If it is molecules, if it is n molecules, it will be n here. V minus n factorial into n factorial. This is the case because only one molecule can be placed at one site. For that particular case, we have this formula. Now, so that gives us 100 factorial by 98 factorial into 2 factorial, which is 98 factorial, and 98 factorial goes here, and 99 into 100 by 2, 9900 by 2. So 9900 by 2 is nothing but uh, 10,000 by 2 is 5,000. 5,000 and okay, so it will be 4950. 4950 number of states. Total, these are total number of states. Now we have to calculate the non-adjacent states. So initially I would have calculated non-adjacent states, but it would be difficult, unlike these adjacent states, to calculate. So firstly I calculated this, then calculated total. So we can now find this by subtracting 4950 minus how many there, 180. So this will give us 4850 minus 80. I think 4730. No, this is not correct. 4770. So these are the number of microstates corresponding to equal to 0. Now let's solve the next question, which is assertion and reasoning type question. So here, internal energy don't confuse whenever it is given with some other. If the internal energy is denoted by some other letter, uh, that's okay. So here it is given. The assertion is that internal energy is a well-defined function of entropy S, volume V, and particles number n in thermodynamics. Well-defined function means the internal energy and entropy S have a unique relationship. Like for a given entropy, the internal energy will have only one value. So for every entropy value, there will be only one internal energy value. And the reason given is that entropy S is a monotonic and concave function of E, ensuring a unique relationship between E and S. So monotonic is a one important term to understand. That means in physics we see the relationship between quantities, like when a parameter is increasing, other parameters will vary according to that. In some cases, we find as suppose x and y are two parameters, and as x increases, y will increase up to a certain extent. Then further, as x increases, x will decrease. This is not the case for monotonic. Rather, the monotonic case is as as long as x increases, the y will also increase continuously. So that means it is a monotonic relationship. And also a reason is it is a concave function of E. S is a entropy. S is a concave function of E. So yeah, we have to prove that. Um, okay, so as it is monotonic, uh, actually, in fact, S and E are monotonic. So the reason is the correct explanation to the assertion, but we have to see whether reason is also correct for concave function, or whether entropy S is a concave function of S or not. So for that, we have to calculate. Uh, See if there are two variables, to find the relationship between them. We have to find this. In this case, d square s by d square. We have to find if it is less than 0, then it is concave function. So here see the relationship entropy S, so which is a dependent variable, function of E, which is independent here. Independent in the sense uh, it's not independent it is dependent of other variables like temperature, etc. But yeah, the meaning here is that S depends on E. That's all. So in order to calculate this, we have to, and we know that internal energy is a state function. It depends only on the state variables like entropy, volume, and number of particles. Now, for a given set of entropy, volume, and number of particles, there is a unique value of E. And from thermodynamics, we know the relation uh, that is 1 by T is equal to ds by dE. Yeah. Now, when we double differentiate, This will be is equal to minus 1 by t square and dt by dE. Here E is the internal energy. Um, and we knew that d is equal to cv dt for a stable at constant volume. So I mean to say that for stable thermodynamic system, cv is greater than zero. Why means, see, in order to raise the temperature, it should absorb the heat. So, yeah, in order to raise the temperature, it has to absorb the heat. So that means Cv is greater than zero. Cv is greater than zero, and 1 by, if Cv is greater than zero, 1 by Cv is also greater than zero. And we know from here that dt by dE, from here dt by dE is 1 by Cv, which is greater than zero. So here dt by dE is greater than 0 and temperature is also greater than 0. So I can write like this is positive and 1 by T, temperature is anyway positive. Before the product of two positive things we have negative, so this whole is less than 0. That means it is a concave function. Suppose we have in generally, so yeah, hence it is a concave function, and the monotonic nature also we know, and it will become obvious as we go along why the entropy and internal energy relation is a monotonic function. By the way, when the main essence of the monotonic in the reason is that this implies that for every e we have unique value. For example, let me draw two graphs, one of monotonic and non-monotonic. So, okay. So assume that this is a straight line. We have y and x. Y is depending on x, and it is going in the straight manner. Assume that it is straight. So we have only one value for one x value. We have one y value at any point. Please assume that this is straight. And in this case, let me like this x and y. So this is monotonic because unique value we have. And this is non-monotonic. Now, okay, as the x is y increased and then decreased. So for the same y value, means for two x values like x1 and x2, we have the same y prime value. So this is non-monotonic and this is monotonic, and that's what given in the reason. When it is monotonic, If this is true and we know that it is true, will you will understand for the next things why it is true. So that implies is a well-defined function of entropy S and volume V and particle N in thermodynamics. Because internal energy depends on the volume and the number of particles, etc. E depends on S, V, and N, and S depends on E, V, and N. Now, another thing is that concave and convex function. Suppose we have a function y is equal to uh, e power x. Now, when we differentiate one time, we get e power of x, we get e power of x. So, this is greater than 0, means as y is increasing, this will become positive. So, this is a convex function. Now, we have another function y is equal to minus x square. Here y dash is equal to minus 2x and y double dash is equal to minus 2, which is less than 0. So this is a concave function. Let me plot them. You will. So what does y is? I'm just plotting for this one axis. You will understand from that x, y, e power x. We know that e power 0 is 1 and e power infinity is infinity, and so it just goes on like this. This is a convex function because y double dash is greater than 0. And I will on the same, um, I will write here this is e power x. I will plot minus x square. So minus x square. Uh, when y when x is equal to 0, y is also 0. When x equal to 1, y will be minus 1. When x equal to plus 1, y will be minus 1 here. And when x equal to minus 1, then also y will be minus 1. So this comes something like this. And this is a concave function. And in order to find that, we have to calculate d square y by dx square. So also remember this monotonic is very important term in physics. Wherever it is monotonic, that means that every time there will, as x increases, y will increase. It can be like this also. Another example, this can be also monotonic function, but it can't be a curve like this. Here this is also a monotonic function, e power x, which keeps on increase. Now let's focus on the fourth one. A substance has an entropy given by the relation S equal to A, where A is a positive constant. Using the uh, thermodynamic requirement that entropy is an extensive property. So basically, it is known that entropy is an extensive property. We are aware of that. Determine the constants on the constant BCD. And if a system is doubled energy, volume, and number of particles, verify how the entropy scales and find the values of BCD that satisfy the extensivity. Okay. So entropy is an extensive property. What does that mean? That mean if suppose volume becomes uh, doubles, then S also will be doubles. Okay. Yeah. Now, in order to find the constants B, C, and D, what we have to do is let's do this. In order to find the constraints, let's make E comma V comma N lambda times the previous value. So in the first case, sorry, S is equal to A. Now when we make um, when lambda E and lambda V lambda N, this is the scenario. We get S equal to, sorry, here not just V but E, V and N. When E, N and V, all these three doubles, then S will be double because S is function of E, V and N. Okay. Now in this case S will be is equal to A. I am taking lambda outside, then it will be B plus C plus D, E power B, B power C and N power D. Now compared to previous case, when we done lambda times, then it should be S will become lambda times. So previously we have S equal to, so I'm writing this as S2, second state. S1 is A, E power B, V power C and N power D. So S power 2 should be lambda times S power 1 because we have um, increased to lambda times, made lambda times of E, V and N. From this we can get that b plus c plus d is equal to 1. This is the constraint that has to be followed. This is the thermodynamic. So this constraint has to be followed. Then only the entropy is an extensive property. This is the thermodynamic requirement that entropy is an extensive property, which it is. I'm underlining here. This is the constraint. Now what are the individual values of B, C, and D? That depends on the system. Uh, let's go to the fifth problem. Now we have here four distinguishable particles. That means four are different particles. Four particles are different, distinguishable. Indistinguishable means identical. So let me name those particles as A, B, C, and D. Now then these can occupy one of the three independent states. So there are three states which are independent. Determine the total number of possible configurations assuming that each particle's position is an independent degree of the freedom. So what does this line independent degree of freedom mean? That each particle's position is a independent degree of freedom. So just copy from each two freedom. Imagine that I have placed here and giving what does that mean? That means occupancy of um, one particle does not affect the other, does not affect the position of other particles. Okay, so we have three independent states. Let's put them like, for example, this is one state, second state, and third state. Now we have four distinguishable particles. See, the four particles can occupy these three. Um, so G power n. I'm writing the number of microstates available. That is G power n. So here G is the number of states. G is number of states. N is number of particles. So this is a basic probability um, thing. We can also calculate that. For example, I will take just to simplify. I will take two particles and three states. Let's say now here two particles are distinguishable. So A B I can take. So I can arrange like this. Let me take space between these three states. I can arrange in this manner. I can put A, B and nothing here. I can put A and B here, or A and B here, or B and A here, and here nothing, and B, A here. So this is or nothing here and AB and nothing here. AB we had A and B. All the possibilities here are done. Now I can put B here and A here and nothing here. And AB and sorry. So here nothing. AB we have done here, and B we have done, and A and B. This is also another case. So A, B, A, B are done here when we put nothing. So each time we are getting three times nothing. So here we are done with three times nothing. Uh, yeah. So A, B, nothing, B, A, B. And next thing is that A, B or nothing, and we can't put A, B here. So A, B I have placed here. So what are the remaining possibilities? So we have like this. Each time AB 5. Here also we got 5, and here also we got 5 different possibilities for different constraints. So what is the total? 1, 2. If you count the number of microstates, 1, 2, 3, 9. So we got total 9 microstates. That means uh, the number of states that are available for us is 3 states, and number of particles are 2. So that's we got 9. And in the so this is the formula for us g power n. You can also cross check with some other example. Now here we have 4 distinguishable particles. That means g is equal to 4, and number of states are 3, and also given that each particle's position is an independent degree of freedom. That is, if one particle is positioned at first side, the other three particles also can be positioned, because each particle's position is an independent degree of freedom. Now from this we get number of microstates is equal to g power n, which is 4 power 3. 4 4 is 16, so 64 available states. If it is 5 distinguishable particles having 4 independent states, then this is for so I'm just putting it as first and second part. This is first part of the question, and this is second part. So the second part of the question is G is equal to G means number of uh, sorry, here we have wrote mistake. N is the number of particles and G is the number of states. So G is equal to 3 and N is equal to 4. So it is 3 power 4, 81 states for the first case. And for the second case, G is equal to 4, N equal to 5. So states available in this case is 4 power 5. You may calculate that. And also general expression is this one, the third part of the question. And fourth part of the question is we have to repeat for identical particles. Mm, so for identical particles, in the first case, what is the G is equal to 3 and N is equal to 4, and these four are identical particles. So I can write A comma A. Now let us do this for three states like this. Uh, First state, second state, third state, and two identical particles A comma A. Just an example to derive the formula. So I can put two A's here and nothing here, or I can put one A here, nothing here. Uh, the other thing is I can put nothing here and two A's here, nothing here, A, nothing here, and two A's here. So you can see there are three. So total one, 2, 3, 4, 5, 6. So six states we got. So the formula for this is that um, G plus number of states is G plus N minus 1 factorial G minus 1 factorial times N factorial. So for this case, let's check whether that's right or not. In this case, G is equal to 3, N is equal to 2. So it is 3 plus 2 minus 1 factorial by number of particles 2 factorial, number of states 3 minus 1 factorial. So basically 5 factorial by 2 factorial into 2 factorial. This will 3 plus 2 5, oh sorry, this is 4 factorial. So 4 factorial by 2 factorial means we get 3 4 divided by 2. This will give us 60. Now for our main problem, we can see the number of states is 7 minus 1 6 factorial by G is 3, so 2 factorial, and so basically 5 6 30, so 15 states. And for G is equal to um, what is the second case? G4N5 equal to 4, N is equal to 5, and do remember this formula. This is quite hard. Like even if I calculate six states, it is something difficult to trace the derive the formula. It is not straightforward. I mean, so you may remember like G plus N minus. So this is applicable for other problems in probability. So this is something more useful in probability as well. 5 plus 4, 9 minus 1, 8 factorial by G minus 1 factorial. That is 3 factorial, and then straight away in factorial. 4, 6, 7, 8 divided by 3 factorial is 3 into 2. So it is 56. This is how we. So I hope every concept that I taught here regarding entropy is clear. Entropy and microstates. This is a quite good introduction for microstates and entropy, and we will see more about entropy, microstates, and further concepts in the next lectures. Thank you so much for watching, and please do subscribe